this? Okay. So if we're in this screen, you'll notice that there's a bunch of how-to models shown here. What I'd suggest you do is to go to Help Example Models, okay? And it will take you to a kind of a different list here. And SIR agent-based is kind of moved around. If you go up to Healthcare up here on the left-hand side and you scroll down, I think you'll, oh gosh, they moved it for this version. Sorry, folks. So you go there and how-to models, and it's under how-to models, sorry, SIR agent-based. I got the two versions confused. So, so how-to models, click here, and then it will be on the right-hand side. Apologies, they are constantly adding to these models, and they shift them. Okay, so how-to, and then it's alphabetical SIR agent-based. I'd like you to click on that to open it, okay? And when it opens it, it's going to open an environment here where you're going to be able to see components of these models. Does anyone recognize the general shape of this environment?
This looks like a clip smash.
Yeah. That's true. It has a certain MATLAB-esque feel to it, but it is Eclipse-based. This is an Eclipse RCP, Eclipse Rich Client Platform application. And you'll find sort of Eclipse functionality popping up at a bunch of different places. Over here on the left-hand side, you'll see information on the projects. It's a hierarchical decomposition. You'll probably only have one project loaded. I have more because I work on this for other reasons. So they'll be down here at the bottom, there'll be SIR agent-based here. Now, we're going to do a quick walkthrough of this this model. This model is focused on spatial spread of an infectious disease. So the idea is that you're going to have someone infected up front, and it's going to spread. It's going to spread over time to neighbors within some space. And the individual state is going to evolve, and each of the states of the people infected are going to evolve, and as it spreads, they're going to go through a state where they're effective, and then they're going to be recovered. Now, this shows infection. It could just as well show someone getting interested in purchasing some particular item and telling their friends about it, and then those friends getting interested, and then at some point it's old hat and they're no longer raving about it. So they buy an iPhone 5 and they're talking about it, etc. What's going on here is that it's going to spread to 4 neighbors of each person in a structured way, okay? Or it can spread. It's not deterministic. It's going to be stochastic, north, south, east, and west, okay? So let's go see how this is kind of realized. You'll notice that this has several components. To avoid distraction, I'll kind of drag this up here so you could focus on this. First is a main component, and main provides a stage, as it were, on which it's a global environment on which these agents can circulate. And then there's some logic actually associated with that. And within AnyLogic, there's a common practice of kind of putting things over here on the left. So if you scroll over, it looks deceptively empty, but you see over here on the left there's some components. And we'll go through this in much greater detail, some of the conceptual distinctions, but broadly there's a set of parameters which dictate assumptions. They communicate sort of what to assume about the total population size or about the contact rate on a per, in this case, scenario basis. So it'll allow you to say, hey, let's see how it operates with a large population, with a small population, with a high contact rate, with a low contact rate. Then there's some variables which keep track of quantities changing over time. Typically, these parameters aren't changing; they're static assumptions. They can change, but it's less common. And then we have variables, and then we have a population of people. Okay, where these people are a collection of people that exist, and we're going to see how they interact within a space, a structured space, in just a minute. So these individuals within that population are agents. We're going to call them agents. And if you click on population, what you'll see is that there's a specification of the size of the population. And in this case, where do you think that population size comes from? Anyone want to hazard a guess? Where would it figure out the population size if we go look at people? Well, it just gets it from this parameter, total population. Now what you see here is a reference, initial number of objects to this total population. Now, that just looks like you filled in a name here, but what you'll find is within this package, a lot of these times it just looks like a name. It's actually an expression. It's a Java expression. Okay? So really, this framework is chock-a-block full of places where you fill in fields with what look to be numbers or names of a parameter, but it could just as easily be a general expression, a call to a function or what have you. So this people is going to be a population of people, a collection of people. And a model like this could have many of these. Okay? In this case, it's only one. It's dictated by the total population, and there's some parameters which could be specified, and you can compute statistics over it, etc. But let's go take a look at person. Now, if we double-click on person, what we see here is a depiction of information about a person's state, their characteristics at a certain point in time, some of which evolve over time, and further, a depiction of sort of the rules governing those dynamics, the rules governing those changes that take place at an individual level. So specifically, what is this? Who can describe from computer science background or any other background? What is this here? It's a it's a finite state automaton. Yeah, it's a finite state machine. It's a state chart in UML. It's a UML state chart. And what we see is we depict an individual as falling into one of three states. They're susceptible, so they can get infected. They're infectious, they can spread the infection, or they're recovered. And as I said, this can apply just as well to a contagion of ideas or of affect, of sort of enthusiasm or rumor spreading, as it could to a pathogen, to an infective biological agent. So let's take a look at this more. You'll notice also there's a variable here. Where did we see this? This V, where did we see that before? We saw it just a minute ago where? We saw it up in main. And we saw main also has variables associated with ed that evolve over time. Those are the counts of the number of people susceptible, infected, and recovered, which are actually just convenience counts, so it can keep track of that more quickly. It can always just count it up at every so often. And there's a variable here that gives the person's color. Now, as you might expect, color would be a reference to an object of type color here. That's Java standard libraries for color. And these state charts have some textured dynamics associated with them, associated with these transitions. So, for example, this infection transition. Maybe we'll first look at a simple one. Look at the recovery transition. Here, this is dictated by a rate. We're going to talk what this means. This will be one of the things I really want to hammer home in this class. And it cuts across the multiple sorts of simulation. You see it in system dynamics, you see it in agent-based modeling, you see it in discrete event modeling, what this rate really means. But fundamentally, we have a certain process. There's a certain chance per unit time of someone going from this state to that state, and it's given by 1 over this average illness duration for reasons that will derive why it's 1 over that. But it turns out mathematically, this transition is associated with an exponential distribution, and the mean time to transition here is 1 over the rate of transitioning and vice versa. Okay, so this is a rate, a chance per unit time. It's like a 1% chance per unit time they'll transition if the average illness duration is 100. Somewhere we can go and look up, is that 100 days, 100 months, but I won't go into that right now. Okay, so here's a transition that's dictated. It's a memoryless transition. Doesn't matter how long they've spent here, they just have this certain rate of leaving, okay? And that will be associated with what we call first-order delay in system dynamics, for example. But let's look at some more sophisticated transitions. Let's take a look at that infection transition. How do they get infected? Well, this is triggered by a what? Triggered by you could just read it off there. What is it triggered by? Yes, thank you. Put me out of my misery. It's triggered by a message. And it's triggered, in this case, unconditionally. We could, in a bigger model, this is a toy model. In a bigger model, you might have check what the message says. You might say, okay, these sorts of messages relate to these things, these other sorts of these other things. You might flip a coin if you get the thing. In this case, it definitely is going to happen that if this person receives a message of exposure to this illness, ba-boom, they will make this transition. Now, where does that message come from? Anyone want to hazard a guess? Okay, so so under what condition does that message apply? It's only if I am a what? Susceptible that message. If I'm infective already and a message comes in, it's not going to matter. It's going to fall on deaf ears. If I'm recovered, it's not going to matter either. But if I'm susceptible, because this transition leads out of susceptible, hey, it may make a material difference. And in that case, I will transition in this fashion. Okay, so that will transition me. Under what conditions would I receive a message like that? Who do you think sends that message? Yeah, an infectious person. And that, ladies and gentlemen, sort of finishes the little component of this, because if you look at infectious, there's this so-called self-transition. This is a transition where periodically at a certain rate, it sends a message to a randomly selected neighbor. Okay? Where neighbor has a very specific meaning here. We're going to learn later that there can be neighbors in 4 directions, neighbors in 8 directions. With looking at north, northwest, northeast, etc. But there can also be what might be called informally neighbors, but are actually called connections in AnyLogic within a network. So you could also send messages to people in a network, or just anyone randomly selected through the space. Okay. Okay. So that's all well and good. But there's something we haven't checked out. I mean, what sort of space are these in? We've seen these people are in a population. If we go back to Maine, and it's very important that you conceptually have in mind what you're looking at. We were looking at person, the characteristics of a particular person. Let's go back to Maine and look at the environment. We didn't really poke around here, but if you look in the advanced characteristics of the environment, we see, oh, this is a discrete 2D environment. We're not doing anything fancy with 3D environments here. We'll see that there's a real distinction between continuous and discrete environments we're going to get into conceptually. But fundamentally, this is an environment of a certain width and a certain number of columns, certain width and height, and a certain number of columns, which are distinct from that width. In this case, the width and height relate to pixels. And the columns, it turns out, there's enough of them on one-to-one basis so that each of them is a pixel also. Okay? And you'll notice that it's an arranged network, which basically means it's a square grid in this case. Okay? You'll notice that there's some other opportunities here, and there's some ways to specify networks. In this case, we're not dealing with networks. We're dealing with spatial connectivity. Okay, so having seen that, let's go run something like this. Let's go run a simulation, for example. And if you right-click on simulation and you do run, I'll do that again so you folks can follow. This is going to be unusually tutorial. Right-click on it and do run. Another way to do it is you can do it through this button up here. Okay. We've defined a model. We've looked at the model, and we haven't gone through all the details, but basically we've seen it specifies sort of how things work in this simplified view of the world. Now what we're going to do is we're going to run a scenario. We're going to run a scenario where we take that model and we simulate it out over time, and we see what its implications are dynamically. When I say dynamically, what do I mean? Can anyone tell me? Say dynamically in this case. Dynamics, the term dynamic has somewhat different meanings within different areas of computer science. What does it mean in this case? If I say I'm going to simulate this you know, I'm going to run it out dynamically. What do I mean? I mean run it out over time. Yeah, yeah, exactly. So I'm simulating this thing over time, and I'm going to see its behavior. And I'm going to see its behavior, ladies and gentlemen, with certain assumptions. So if I actually went and I looked at this scenario and I went down to Parameters tab, you'll see in the Properties window, there's a Parameters tab. There's assumptions here. Okay, what's the illness duration? What's the contact rate? What's the infection probability? I can modify those. In this case, I'm just going to leave them constant, and I do run. Right-click on it and do run, and then I press this run this model. Okay, and here, ladies and gentlemen, we see an infection spread. Do you see that? So one person started infected at the very beginning of the simulation. That person was down here, and it started spreading out. And the color, although I didn't go and I didn't trace the logic for it in great detail, the color is dictated by the person's state. So that color variable, if you go and you poke around a little bit more, you'll find that the color variable is actually updated when a person goes into a state. For example, it says, for example, color equals red. Do you see that? For example, when they're in this state or when they're in this state, color equals gold. So basically that color variable is being used to kind of record what state they're in. And through a bit of finesse that I'll show you later, it's actually really easy, we're actually making that the pixel's color, okay? So here we have color-coded, and what we see is an interesting phenomenon. So can anyone characterize what they see there? So I'll run this a little bit more. I suspect many of you are seeing this in your screen too, so you're not relying on this. But what are we seeing? And why are we seeing it? What's going on, crudely speaking? Okay, good. And the people who are infected at the current time, the people who are infectious, spreading the infection, where are they concentrated? Yeah, near this boundary. How about these people in here? Are they infected? Are they infectious? Are they spreading? No, they're recovered now. They're past their infection. How about people out here? They're susceptible still. They haven't been touched by it yet. And why do you think it's so? Broadly speaking, what shape is it? It's roughly sort of an element, sort of a subpart of a circle. Yeah. And why is it not perfectly circular? Why do we see these irregularities and so on? Anyone want to hazard a guess? Well, we actually saw the answer to it earlier. Well, a lot of the answer. It's actually not the, yes, we could piece together the components. First of all, this is to a random neighbor. So we're not infecting everyone in a deterministic way around us. We're sending messages to a neighbor, and we're sending them at a certain average rate. There's stochastics associated with that. There's, sometimes we'll be sending more messages. Some people will have sent more messages. Some people will have sent fewer. And whether that message infects anyone will be a matter of what those people next to us, what state they're in, right? And then also, when we saw our recovery, that also was at a certain average rate. And it's actually computing stochastically, okay, okay, when is this occurring? Exactly at what time is this person recovering? It's actually drawing from a distribution at what time they're recovering. So, in short, there's some uncertainty about how long they remain infective, and that's important because it relates to how many people they infect, right? If they stay infected for 20 time units, they might infect 20 times as many, or twice as many people as if for 10 time units. Okay, so we can run this thing out, and it's going to be spreading out. And you'll notice there's all sorts of information down here at the bottom. And in fact, you can tailor what information using this little triangular thingy there. One of the things that's reported here is events per second. How many events it's handling. We're going to talk about events because they form a critical underpinning for this sort of simulation, as well as discrete event modeling. They kind of are the thing that make the world tick. This thing is not stepping through at a fixed set of time points. It's instead handling events whenever they occur. If things are happening really, really quick, it simulates at the level necessary, fine resolution. If they're occurring far apart, it handles that. Okay, so this thing is spreading out. And you'll notice the time. Oh, the model time isn't shown. If we want to show model time, go down here and we do model time. Boom. Okay, here's the model time, 3:47. Now it says suddenly infinite. What does that mean? Why did it say infinite here, model time? Well, there ain't nothing left to do. There's no events happening anymore. Without an event possibly happening, there's going to be no other events triggered. So as far as it's concerned, it might as well have gone forward to time infinity. There ain't nothing changing. Okay, so that's a little bit of something. We've sort of played through this. Now, I'm going to ask you to do some experiments here. So the first thing I'm going to do is I would like you to follow me when I added model time into that boundary. So I'm going to go back and do that just so you could see that a little bit closer. I think many of you saw it. If you click on this and you do model time, you'll see model time being added there. And I'm going to run this. And let me ask this. How long does it take to get to the boundary? Did anyone time it? Let's see how long it takes to get to the, say, the upper boundary. So it's spreading up. Its center was probably somewhere around here, just sort of forensically. By the way, where is this circle programmed in? Did I program that circle into here? Is there some place I told it, create a circle of expanding radius? Did I tell it? Where did that come from? It emerged as a property of the system through the interaction of a couple different things, right? The connectivity of people and sort of this infection, the way the infection is transmitted and handled and stuff like that. That's not programmed in. That's going to be one of the first examples of kind of an emergent phenomenon we see. Those emergent phenomena can sometimes be very surprising. Sometimes you might anticipate it if you sat back and thought about it, and sometimes it can be very, very surprising. But the point is the behavior of the whole transcends the behavior of any one component. There's a very different behavior coming from the whole. Okay, so it's sitting there about times 300, eh? 300? Okay. So now let's go modify some assumptions. Okay, so we're going to go and modify the model. Okay, so right, we're going to create, so I think in your model, mine has already been modified like this, but I think yours is not. So let me delete this guy here. And what I'm going to do is create another scenario. So this is kind of what we'll call a baseline scenario, where we kind of are using the default assumptions, okay? Now let's go and let's create an alternative scenario, a scenario with alternative assumptions in it, okay? So how do we do that? Well, right-click here, do copy, and then right-click on the whole project and do paste, okay? Kind of a familiar Eclipse thing for those familiar. Now, a new thing will come up. We'll say simulation 1, and it'll put a little X indicating an error next to it. And that's because we have to tell it, okay, what's your main class that you're depending on? And so you have to go in the general properties and choose main, okay? And let's give this guy a name. And I think the name I gave it was slow recovery. So in short, folks, what I did is I right-clicked here, did copy, right-clicked up here, did paste. You folks have enough savviness, you know, you Control C, Control V. I mean, you don't have to follow slavishly. Okay, so we're going to go up here and we're going to make this slow recovery. Okay, slow recovery. So this is going to be a situation where we're going to have alternative assumptions. We're going to see what this assumptions yield. Okay. So these assumptions are writ large in these parameter values down here. There's actually a parameters tab. Okay. And this parameters tab is going to tell us what to assume. So we're going to assume here that the illness duration goes up from 15 to 50. So from 1.5 to 5.0, in other words. So, in other words, this original scenario where we made certain assumptions called simulation, that's the baseline with 15. And for this alternative, we're going to be running the model with a different set of assumptions, different set of parameter values. We're going to be parameterizing it differently. We're going to have a longer illness. Now, generally, what would you expect from a longer illness? I mean, what is that going to lead to? If people here are staying sick for longer, how would that affect things, do you think?
The infection might spread faster because they're given longer time to spread. The red wave visually will be much longer.
Exactly. Okay. So yeah, that might be very much what we expect. I mean, the red is going to be thicker because they're staying infected longer, and normally you would think that, you know, someone circulating for a longer period, if it takes you 2 weeks to get over the flu's infectious period rather than a week, you're probably going to infect more people, right? So you might think that. Now, I noticed that your words were hedged, and as well they should be, because we have a very particular situation here. But let's go run this. Okay, so I'm again going to have it display time down at the bottom. Boom. And what we see very much matches your name? Alex, what Alex was saying. So you'll see the thicker kind of ring around here, and you'll see that these individuals in the center, you know, many of them remain ill long after the ridge has passed. So, great question. Is it spreading a lot faster, do you think? Okay, we have to be a little bit careful because there's simulation time, and then there's sort of the time necessary to simulate it. The simulation time is shown here, and just because it's not going faster visually doesn't necessarily mean that it's not going faster in terms of simulation time. But what you'll find is that indeed it isn't going too much faster. So you'll notice also in fact it seems visually to be going what? I mean, just at a visual level, it seems to be going slower, I would say. It's crawling. And that's because, ladies and gentlemen, it's actually handling more events than it was before. Why is it handling more events? There's more sick people sending off these things saying, hey, you're exposed, hey, you're exposed, you're exposed, you're my north, south, east, west. So there's actually a lot more work for it to do right now that's causing it to kind of drag its feet. But again, I mean, that's kind of a matter of performance. The time is creeping along. And you know, we could let this thing run out, but the short answer is it's not going to get there that much quicker. Why not? Why not? As we'll see later in this course, there are plenty of models, simplified models of this, which assume that people mix throughout this population very readily, where actually you would think that these people should be infecting twice as many people. So what's different here? Why isn't it spreading faster? Yeah, well, it's only the poor people with the border matter. You can only infect them once, right? You can only infect the ones around you once. Once they're infected, that's it. And so there's kind of a saturation effect, an effect where you know, there's only so much you can accomplish, and by staying sick longer, you're not going to be spreading it that much more. There is going to be some boundary effect. Like, there will be cases where, you know, just by chance someone stayed susceptible and actually here now they're going to recover. So there's going to be some marginal effects of unlikely cases which are now, you know, even less likely. But still, it's not appreciably faster. You'll see it's getting up to about 300, and this is about when it passed it last time. A little bit faster, but how much could we rely on that either? This is going to get to some issues we're going to be exploring. So the first model, we clocked it in about 300, 301 or something. This was 296. Can I say that this model is faster? Like, in other words, the infection is spreading faster? Okay, why not? Why would I have to be careful about that?
That's the statistical argument in your sample space is far too small.
Exactly. So that's fundamentally, I'm making a statistical claim. I'm saying this is faster, but there's stochastics. There's uncertainty. There's bars of error around those things. If I ran it 10 times, I'd get 10 different answers, and there'd be some variability. And so to really test this, I'm going to need to run this thing many times. And we'll see that AnyLogic provides exactly the tools to do that, so that you could start to reason with greater confidence that reason about whether these differences are statistically significant or not. So we're going to see statistics coming into this picture some in terms of developing confidence for these sort of models. Okay, so that's all well and good. Let's do a couple more things here. First of all, what I'd like you to do is we're going to now do something quite different. We just added in a new scenario. Now what I'd like to do is to add in, to change the model, to change the model structure. When I added that new scenario, what did I change? What was the difference between slow recovery and simulation? I changed the parameter assumption. Did I change the model? Not really. I changed sort of the assumptions I use with that model. I didn't change the model structure. I didn't change sort of the flow. I didn't add a new state or change how the transitions go. Now I'm going to do that, folks. So let's add a transition in from recovered back to susceptible. Okay. So now we're doing something more fundamental. We're actually changing our assumptions, sort of how things play out. So what do? I go down to do this. I go over to the palette on the right-hand side, and I drag from a transition into here. And I'm going to want one part of it to come from the recovered. And now I can actually just go drag it up to susceptible. Okay. So in short, I have to be in the palette, go down to state chart, and drag the thing that says transition in there. Okay. And then I drag it to go from recovered to susceptible. It's important, folks, that it be green on both sides, because that actually means it's connected. If it ain't green, it ain't good. So if it's something like that, it's not connected. That looks obvious in this case, but there's cases where it actually looks like it might be connected, but it's not. So it should be green. So drag in, transition, connect those. Okay. So now we're going to have a transition back here, and what I'd like to do is to associate this, call it waning of immunity. So people after a certain amount of time are going to lose their protection, their immunity against the illness. And I'd like to give it a timeout of 100, okay? So this is going to be a timeout of 100. Now, those of you who would like to invest in aesthetics, you can actually, for example, double-click in the middle of this transition and pull it out so it goes out there, so it won't cross over. And you can click arbitrary times and sort of shape it as you see fit. But that's not a logical issue of connectivity. It's just the kind of aesthetics of how it draws it out. Important for communication, but not for function, how it's actually running. Okay, so what I did is with this new transition here, I set it to be a timeout of 100. Okay. So and I should call it something meaningful. Waning immunity. Okay, so after a certain amount of time, our immune system forgets we're infected. There's many infections. Pertussis is like that. We forget that. So these days they're recommending 8 shots over your life for pertussis to protect you because your immune system forgets these things. Okay, so and the same thing with some phenomena. The same thing with some ideas. They sort of come around. Here we have this, and we have a waning. Okay, so how is that going to affect things? Does anyone want to comment? So now we're going to have people becoming susceptible again after a certain amount of time. What should we see? How will it be different? How is it? Okay, so are we going to see entirely, what are we going to see sort of halfway through? Are we going to see an entire, the center, instead of being gray, will be yellow? Okay, so that's a good hypothesis.
We're going to start seeing ripples within. As the sphere goes out, there's going to be a core personnel that become susceptible again. Then they'll get infected. And along, as the infection spreads out, there's going to be a ring of people that went from recovered to receptacle, then they're susceptible, and they're going to be infected.
Okay, okay. So that will be a hypothesis. And under what conditions would those people in the center get reinfected? Essentially, you talked about a second infection.
Yes.
Under what conditions will be needed for them to get reinfected? There's got to be a nearby infection. So it's going to depend on. Yeah. Okay. Okay. So let's run it. Let's run it first with the regular simulation, not with the slow recovery. Now, okay. Very important conceptual point here, folks. These scenarios were originally defined with the older model, with the original structure. But now when we run them, they're running with the new structure. So it's not like they remember what model structure they were defined with. So we got to be a bit careful here. When we go run in this original simulation, it's running with this new structure. Okay, so what do we see here? So it's spreading out, and don't really see too much difference here. There's oh, okay. Okay, so Alex had a point there.
The timeout's a lot longer than I thought it was, but there is a little
Yeah.
difference.
So what are we seeing here? These folks in the center, in this ring of red, how are they different than those folks? These folks in this ring of red are being what? How are these? The situation they're in is different from this one in what way? They're being reinfected, exactly. And these guys here in this internal yellow have been infected once, but not twice yet, right? Sort of chasing up. And here we're getting sort of a third wave here. So, folks, if I ran this for a long time, do you think this would go to time infinity with no changes? No, we're going to start to see these sort of patterns. Why these sort of islands, by the way? Why are these kind of weird islands of red here? Where are those coming from?
Seems to be from people that had a long recovery rate, and so they remained sick, and then while people around them were getting better based on infection spread.
Good, good. Okay, so what you're doing is you're creating these hypotheses that kind of about why we're seeing certain phenomena here. They're actually quite similar to what we might do when we see phenomena in the world. But now we have a tool that allows us to actually examine those hypotheses. So, for example, let's investigate the impact of the impact of how long people stay infected. So let's look at slow recovery. How will this be different? Anyone want to comment? If we go look at slow recovery in the same way, how would that be different? Are we still going to see those rings? Okay. Okay. Okay.
Since they can't be infectious and susceptible,
okay. So
we might get the case where everyone is infectious.
yeah. Okay. So here they're coming in, but what's happening here? Are they reaching a very obvious sort of ring? Not really. They're getting reinfected pretty quick. There starts to be actually sort of a core of, denser sort of area of infection there, but it doesn't really form a pronounced ring. Now, let's suppose that we were to create yet again, we're investigating things with computational tools, these hypotheses for what we see. So if the hypothesis is correct that it's sort of these long-standing folks who stay recovered or stay sick for a long time that are mucking things up with that original one, let's have one with really quick recovery, right? So let's go create a scenario where we posit really quick recovery. What should we see then? Let's suppose we have illness duration from 15, it goes down to 1. What should we see then? Okay. Okay. So again, to do this, we have to choose main as our thing, and we're going to do fast recovery, and we'll go down from. Okay. So what's different now?
Well, infection isn't spreading.
Aha. Okay. So why is it the infection spreading? Yeah, I mean, okay, so here we are, and I'm saying, what gives, you know? It's time infinity, and we're still susceptible. What's going on?
Cure faster than to spread the disease.
Okay, right. That's actually quite right. On average, they infect less than one person before they recover. And so do you think if I ran this many, many times, it's possible sometimes there'd be an outbreak? Is it impossible that there's an outbreak, or just very unlikely? It's exceptionally unlikely. It turns out that if for that very first person, he's surrounded by 4 totally susceptible people. If there started to be an outbreak, each infected would be surrounded typically by less than 4 susceptibles, and so they're going to infect even less than 1 person. So it's going to typically peter out pretty quick. Okay, so that's the fastest one. Let's suppose we were to do, medium fast or something like that. So we're going to do it again, and we're going to say medium fast, and let's suppose we do it for this one, medium fast. And we do it at a rate of, let's say, go down from 15 to 7.5 or something like that, right? Do you think it will still spread? Okay, is it spreading? Okay, now how is it going to be different? Yeah. There ain't enough people here who are still infective around to infect this. So do you think what am I going to see a minute from now? Yeah. It's going to be all susceptible.
So the infection time is, that's just defined by a distribution, right? That's not a specific distribution.
Yes, correct.
You give an average,
correct.
and then some person
Correct.
might be given an extremely long infection.
That's right. In fact, it's exponentially distributed. So it's going to be distributed as, if we look at sort of infection time for a particular individual, right? It's going to look something like this. So in the mean of it, it's going to be sort of long tail, right? And the mean of it is going to be at 7.5. But actually, most individuals are going to have sort of lower infection time. So some will have very long.
So if we had a population of 3 million, we might see more reinfection.
Yes. If you had enough population, you'd actually see the occasional one, and it would start to spread there, etc. So you're absolutely right. It's a matter partly of how big our space is, etc. Whether, if this was a space that was 100,000 times larger, we'd probably actually get a reinfection and so on. Okay, so that's an interesting indication. What we've actually seen here is a couple of different things. We certainly saw this emergent behavior. I mean, we didn't program in these waves of infection. When I went and I added that transition in, back from this person thing, I didn't tell it there will now be several waves of infection, right? when we first had the model, we didn't tell it, okay, assume a circular ring around this point. And when we changed that parameter to for fast recovery to 1, we were thinking that, man, I would just want to clear it, but somehow the outbreak didn't occur at all. It went to a very different situation. We went beyond what's called a tipping point there. We went to a situation where the behavior has just totally changed. And in fact, that's exactly what people want in this situation. That's why people get vaccinated. It's to try to lower the number of susceptibles around anyone who might come in with measles, say to the Saskatoon airport, through the Saskatoon airport. If you can surround them with enough people who are not susceptible, then they're on average going to infect less than one person before they recover. And even if you had a couple people coming in with measles, it wouldn't stick. At an individual level, there'd still be plenty of susceptibles, but at a herd level, at the level of the overall system, you're not going to get infection spreading. You achieve what's called herd immunity. Okay? So we've seen that, and we've seen that there are these tipping points, situations where the behavior can change radically, qualitatively change, even based on a parameter value. We go from a situation where with the expanding rings of infectives, multiple expanding rings, to a situation where we just have expanding ring of susceptibles alone. Situations where there's really no ring of susceptibles there because it's just this kind of mass of people getting infected when we had too long a recovery. These are really big changes, sometimes qualitative changes associated with behavior due to parameter changes in some cases, and then even more fundamentally with respect to structural changes. So we built a model here that is actually quite interesting in its behavior. Interesting in ways that it forces you to think, ways that you wouldn't necessarily anticipate ahead of time immediately. And that's one of the reasons these sort of simulation models are being used increasingly, because we're dealing with thorny problems. We're dealing with problems which are tricky. We're dealing with problems where the answers aren't simple, where there's a lot of interacting components, and we're dealing with emergent behavior, situations where the behavior coming out of it is very different from the behavior of any one piece. And really what we're doing when we're simulating is we're taking a look at putting the pieces together in a way that allows us to understand how the behavior of the whole is different from the behavior of the parts. We've seen here again and again and again behavior of the whole system that's just very different from any one piece. And simulation is about putting those pieces together, often within scientific investigation, in engineering, but especially in basic sciences, for example, where it's discovery-based. We have a very reductionist approach. We study the individual pieces. We take things apart and study them. And that yields huge insights and a lot of benefit. But it doesn't necessarily tell you anything about how they work collectively when they fit together. And what this is pointing to is that there's a whole science of putting things together. There's a whole science of the behavior of the whole that goes beyond the understanding of those parts in isolation. And that's really important. It means that it's not all subsumed by different siloed reductionist research into this subcomponent, that subcomponent, etc. Instead, there needs to be a science associated with reasoning about emergent behavior, reasoning about systems phenomena that we've seen here. And simulation is arguably the sort of premier tool in those investigations, because it allows us a roof, as it were, under which to let all these pieces integrate together and to ask questions, to investigate things. So, you know, this is the first lecture of a course which will explore this in more detail. I've given just a glimpse of, you know, a sort of a toy model for this. We're going to be emphasizing some of these points in a little bit more detail next time. We're going to take a little bit of a tour of the three sorts of modeling that we're going to be working on. We've seen one of them today. This is the agent-based modeling component. We're going to go take a look at process-oriented modeling, discrete event modeling. And without tipping the hat too much there, what we're going to see there is a quite different situation. We're going to see, for example, a situation where we're modeling a system not so much from the perspective of the individuals in it, although there will be individuals, but from the perspective of the processes that operate on those individuals. So here we might have an environment, for example, and individuals are circulating within this environment, and those individuals are largely sort of interchangeable. They're broken into a couple categories, but they're interchangeable. And they're brought into the system. They're operated upon by various resources. For example, they undergo a diagnosis. There's processes associated with X-ray testing, etc. And they're sort of brought through the system, and resources are required to undergo those processes on an individual. So we have them flowing through, as it were, a set of processes. Resources are required to undertake elements of those processes, and those resources need to be secured and then released. The resources here might involve these various rooms here. You'll see that it's now in the mid-morning, and so more and more rooms are in use. The hospital is growing busy. Some of the rooms for testing are becoming large. So what we're seeing here is kind of a mapping visually of a process behind the scenes, which actually involves sort of a logical mapping. So if we go and we look at this, you'll see there's actually quite detailed process maps that involve moving individuals with resources. For example, a nurse moves a patient to a certain room, and then there's a prepping of that patient, and then they determine if the X-ray is needed for that patient, in which case you seize a resource. And if it's not available, if the X-ray room is being used, you wait for it. There's a queue for it, and then you move to it, and it gets processed. This is a process-oriented modeling. Individuals flow through here, to be sure, but they're largely viewed as sort of interchangeable. They're entities, as we call them, and a lot of the attention is on the resources, sort of what's needed to lower those queues, what's needed to make the flow more quickly. Now, what we're going to see late in the course is we can actually hybridize these approaches. So we can hybridize the agent-based modeling with this sort of approach so that what's flowing through are full-bodied agents that can interact, etc. But this is a very powerful way of depicting sort of processes. And these processes here are in a hospital, but it might be the assembly of a car, where the entities are cars flowing through, or the assembly of an airplane, or what have you in Boeing. And you know, the question is, how can we do that more efficiently? How can we do it more with fewer resources, or what have you? How many resources do we need to function at the level we need to satisfy customer demand? So that's a different sort of modeling. The final sort of modeling involves what's called system dynamics. And here we use tools that are known traditionally as stock and flow models, but are mathematically equivalent to what are called differential equations. So here we have so-called state variables, or stocks, and we have flows between them. And what we're doing is we're specifying actually the value for flows, and the value of the stocks are they're just accumulating the values of the flow over time. So we give formulas, for example, here to the value for this flow. We do that for all the different flows, and then we see emergent behavior coming out of this over time as these stocks and flows evolve. So in this case, it's a simulation of birds and mosquitoes in Saskatchewan, and we can have a certain number of cells in each direction. And these cells, this is actually a hybrid model, so we have cells which are agents, and then within each patch, what we see are some counts of the number of juvenile birds who are susceptible, infectious, and these things are actually changing over time and in ways that are dictated by the flows. So here it's very mathematically grounded. We can actually analyze this using a whole bunch of mathematical tools, reason about its eventual behavior, its equilibria under which it's stable, situations under which it's stable or unstable, and This is a sort of modeling known as system dynamics. These sort of stock symbols. It's extremely powerful, and it also includes a rich set of qualitative tools that can sort of map out a system and gain a lot of insight. So this is the third type that we'll see. So next time, we'll talk a little bit more about motivations, and then I think we're going to dive into the beginning of discussing some elements of system dynamics, okay? So that will be Tuesday. In the meantime, I will send you some download information if you people want to get a hold of the software. And I will further post some of these videos so that if you're interested in looking back, you're welcome to do so. Okay? Okay, so thanks very much. And I'll look forward to seeing you here on Tuesday. And if you could just put the machines in that box, the sort of container back there, that would be great. Thanks.
Would I rather have you sign an override? This is just for
Sure.
for the EP seminar.
Oh, yeah.
Technically, it's supposed to go till 4:50. So
Right.
I'll just
Right. So it's okay I sign it with pencil?
Yeah, oh, well, I think so.
Yeah.
Is it okay for you?
It's okay for me. I just sometimes they. Oh yeah.
So
Okay.
they require
Where do I do this? Instructors.
Yeah.
Okay. So the engineering physics seminar, is that every week? Or every
Yeah.
Thursday?
Yeah, every Thursday.
And basically this just says I give permission for you to play hooky.
Yeah, this is override the time conflict.
01, 03. Okay. There we go.
Okay, cool.
Yeah.
Who's the again? Oh, it's Eric Newfield.
Eric Newfield, yeah. I think that's a routine thing. It'll probably be routed to our undergrad chair, Mike Horsch, but it should be a pretty routine
So you can just submit this to the